Good evening. For those of you who are connected online, thank you for staying with us until this time. And my name is Sarah, and together with Nicholas and Reju, we are presenting our project, The Sound of Failure. Well, companies all around the world every year have to deal with the financial loss and the other consequences from unexpected downtime due to machine failure. And this unplanned downtimes costs are estimated to be around $260,000 per hour in average over all the businesses. And for some manufacturers, it can even go as high as $50K per minute. And this downtime happen more often than you may think. 82% of the companies have reported to experiencing at least one unplanned downtime in the last 3 years, with the average number being around 2. And considering this and all the other consequences that this downtime have for companies, you cannot deliver, you will lose the trust of your customers. And for all of this, it's no surprise that nowadays many companies, as stated by 72% of the companies, zero unplanned downtime is now their number one priority. But the problem is that most of these companies have stated that they are totally unaware when is the due time for the maintenance or upgrade of their machines. They cannot predict it. And for that, we have a solution. Our proposed solution is an artificial intelligence solution to diagnose the machine failure using their sounds. And for this solution, the technology that you need for collecting data, it's cheap and it's really easy to set up. You can use from our research, you can use a microphone array as cheap as around €200 and Raspberry Pi, and that will do the job. And in comparison with many other digital sensoring methods available in the industry, this is a very easy setup. It doesn't need to interfere with the production line in a company. You don't need to plan it in advance or think about infrastructure. You just need to take the sensors to an already running company and put it as close as possible to the source of the sound. And we are hoping that our solution will help the small and mid-sized companies for whom an in-house solution is not actually feasible. So in the next few minutes, I'm going to talk about the approach that we took, including the data set that we used. And then Reju will tell you how we actually implemented this solution. And finally, Nicholas will show you the results, the web user interface that you can actually use to diagnose the malfunction of your machines. The approach that we took is based on diagnosing a broken machine using its sound without knowing how a broken machine sounds like. The thing is that you can go to any company and start recording the sound of the machines when they are functioning, so in their normal state. And in few hours, you have a really good big data set, but you have to wait and wait for who knows how long for a machine to break so that you can record its sound. And even if the company happened to have some record from past, first of all, the size of the data probably is not good enough. And also probably it's not usable because this type of sounds are really diverse. If tomorrow your machine breaks, the sound that it will make can be totally different from the sound that it made yesterday when it broke. So for that reason, the smart approach is to use your machine learning models train on the normal sounds, the machines when they are running and functioning, and then treat this abnormal sounds, the malfunctioning machines, as an anomaly that you're trying to detect from this unsupervised approach. And around 1.5 years ago, the Japanese company Hitachi released the first of its kind public data set from the sound of real industrial machines that actually made this project possible for us. This is a data set that includes the sound of different type of machines, namely valves, pumps, fans, and slide rails. And what's interesting is that the sound of machines are mixed with the background noise that is recorded from real factory environment. And for each machine, you have the good amount of data for the normal sounds, and you also have some abnormal sounds, which, as I stated before, our model is only trained on the normal sounds. So in our training and validation data set, we only use the normal sounds, and the abnormal sounds is only used for testing the model. And the test data set is a balanced data set, meaning that it includes 50% normal and 50% anomalous sounds. And what we do is we take a look at how many audio files we have in the for abnormal sounds, and we take the same number of audio files from the normal sound, and the rest of the files, and these two will go to the test data set, and the rest of the normal sounds go to the training set. And now Riju will tell you that how we are actually doing this.
Okay, thanks, Sarah. So yeah, just a brief recap before we move on. So our aim is to do a predictive maintenance of industrial machines. That is, we want to detect early symptoms of failure or malfunction of industrial machines. And how do we do that? We do that using the sound from these machines. So the idea is that a machine should have a certain sound pattern or acoustic footprint when it is in a normal state. And then when it is in an abnormal or malfunctioning state, should have a different kind of acoustic footprint. We want to build an algorithm or an AI that can understand those representations, but without knowing beforehand how a broken machine sounds like. As Sarah said, it's an unsupervised approach that we take here. So yeah, how do we really do it? So we go from the sound domain to a visual domain. That is, we take the raw sound from the industrial machines and convert it to a MEL spectrogram. And MEL spectrogram is basically a visual representation of the sound. It's a heat map in principle. And on the x-axis, basically there is time, and on the y-axis there is frequency. So you can see how the different frequency components are evolving over time. So one can imagine this as a grid, and each point in this grid is basically indicating how much power a certain frequency band has at that particular point of time. And the brighter the color, the more the power of that particular frequency band. And this is the kind of visual representation of sound that we use to build our model, basically. And basically now our problem has been reduced from a sound problem to a computer vision problem. So yeah, as I was saying, we are reducing the sound problem to a vision problem. Basically, we take the sound and convert it to a MEL spectrogram. As I said, it's basically a heat map of time and frequency. And then we normalize the MEL spectrogram and break that up into smaller slices of smaller duration. And these small slices are what we feed into the deep learning neural network. And the network basically learns representations or patterns from these slices to actually understand what machines sound that we are inputting it. But there are actually two ways to look at this spectrogram. It could be either interpreted as an image, just a 2D representation, in which case you could use algorithms which are good for images, or you could also think of it as a time series. In that case, you could use sequence models. We have tried both actually, and yeah, later we will talk about one of them. So now let's see the algorithm that we want to talk about mainly. So yeah, Sarah already told you that we are taking an unsupervised approach here. And the kind of network that we are looking into are called autoencoders. And what are these autoencoders? Basically, it has two structures underneath, one encoder and then one decoder. What this encoder does is takes the input and compresses that into a latent space. So this latent space basically holds the data, but in a smaller dimension. And then the decoder takes this latent space as input and reconstructs back the original input. But why do we want to put the input in the latent space and then again reconstruct it back? And that is the thing I'm going to show you now. And that is the main principle about how these autoencoders are used for anomaly detection. So let's say we want to train our network to reconstruct apples. So we just want our network to feed in apples and then output apples. And we want that prediction to be good. So we pass an apple through the autoencoder. It predicts back an apple. And basically then what we see is the difference between the decoded apple and the input. So we see the difference. And if it is a good reconstruction, this difference is small. Then we call it a good reconstruction. But then instead of the apple, if now orange sits in our basket, and this is what we now input with our to our network, since it has been trained only on apples, this orange comes as a surprise to the network, and then it cannot no longer reconstruct it. It basically produces a rugby ball, if you would ask me, or a bad orange, or a bad tomato, whatever. But yeah, then when we compare the output and the input, the reconstruction is bad because the network is not trained to understand the input anymore. And that is exactly what we do with sound. We input normal sounds to the network for training, and we train the network just to understand how to reconstruct back normal sounds. So when the network is trained well and we feed in an abnormal sound, or when an anomaly of the machine occurs, the reconstruction error is bad. And that is how we detect anomalies here. So yeah, we have actually tried different kinds of autoencoders here. Convolutional autoencoders, variational autoencoders, and LSTM autoencoders. Here I will just talk about one of the models, which is kind of our favorite model here. So yeah, let's look at some of the results that we obtained now from the variational autoencoder. Yeah, just briefly about the model architecture. This variational autoencoder, basically encoder-decoder structure. The encoder is a convolutional architecture that condenses into a 20-dimensional latent space. And then the latent space is fed into the decoder, which has a convolutional architecture as well, mirroring the encoder. And the loss function that we minimize during training is mean squared error between the input and output, plus a regularization term. And our model trains pretty fast, about 15, 20 minutes on a GPU. Now let's see how the model trains. So yeah, these are the training loss curves. The blue one is for the training data, and the orange one is for the validation data. You can see they train pretty well. We don't really overfit too much in the data. Now let's look at some of the evaluation part. So for the evaluation, we use the test data set. So long, up to now, I was only training the model with normal data. So the model only knows about normal data and how to reconstruct normal machine sounds. Now in the evaluation, we give it also normal and abnormal data. And as Sarah said already, this is a balanced data set for us. We have 50% normal, 50% abnormal. And with that balanced data set, if we look at the latent space, so basically it is a 20-dimensional latent space, but we dimensionality reduct it to a 2-dimensional space for a visualization, then you can see that the normal data, which is the green dot here, kind of sits in a symmetric way. And those yellow points, which are the anomalous data, in this case, abnormal machine sounds, they sit on different space of the encoder. So already in the encoder, our model has learned something to distinguish between these normal and abnormal sounds. And now we feed that to the decoder, and let's see how the decoder gives the predictions. So these are the histograms of the reconstruction loss, that is difference between model output from the decoder, data output from the decoder and data input. On the left-hand side, there is the histograms for the training and validation data, which are only normal sounds. And as we expect, the training is, the reconstruction loss is small here. You can see the histograms are peaking at lower values of reconstruction loss. And then on the right-hand side, we have the test data. The green histograms are the normal test data. And since the machine is trained to understand that, we see a low reconstruction error in the normal test data. But the violet points or the violet histograms here, which are the abnormal test data, clearly separate out with a higher reconstruction error. So yeah, we see that we can already distinguish between normal and abnormal data if we look at the predictions from the decoding space. Now, let us see how our evaluation metric looks like. In this case, we used the area under the ROC curve here. And when the model is trained well, we expect something close to 1. And when the model gives random predictions, we expect something close to 0.5 or even lower. And in our case, the area under the ROC curve is about 97%. And here I remind you again, we are using a balanced data set, 50% normal, 50% abnormal. So if you ask me, the results are pretty good. And now, yeah, Nicholas will introduce you to our user interface a bit. And yeah, let's see a live demo now. So Nicholas.
Thank you. Vijay and Sarah for doing the groundwork for what I can now do. And that is, I will now talk you through our web app, in which I can talk you through the process of failure prediction step by step. So the web page is separated into 4 different tabs, and I will quickly guide you through these. So first of all, let's do a bit of data exploration. So I want to play you the sounds that we've always talked about so far. So we're having normal and abnormal sounds, and I will now play these, and I hope they show in Zoom, but I will also turn the speakers on for the room. So let's hope the feedback isn't too bad. And there comes this sound. Okay, this is a bit quiet. Does it show in Zoom? Is it coming? So I will play the second sound. They are not the most exciting sounds on earth. So I will play the second sound, and maybe we can find out whether the audience can hear them really. Otherwise, I can also describe them. They're not so complex. So I have played those sounds. Now people in the room couldn't hear them, but what you would have heard and what you will hear when you go to the app is that the normal sound will have a tick tock, tick tock, tick tock. So there are 2 types of beats, and it's very repetitive, while the abnormal sound has a disruption of the pattern and only has the 1 type of beat. So we've talked about the MEL spectrograms in the talk, and here we can create them. So there are a couple of parameters you need to set. So I'm happy to answer what they are if anybody has questions later on, but for now, let's just take it as that. So a spectrogram is a representation of what frequencies there are in the sound and how that develops over time. So for the normal sound, we see the 2 types of beats as thick and thin lines, alternating thick and thin lines. And then for the abnormal sound, we see this different pattern, and it's a 10-second long sound sample. So this distinction between a normal and an abnormal sound is what our algorithm should pick up on, right? So let's see in detail how our AI analyzes this sort of sound. So we'll start with a normal sound. And yeah, what's the idea here? So our algorithm is designed to detect abnormal sounds, basically. So we've trained it on a particular type of sound, and it'll be working well on this type of sound. And if something abnormal comes, will expect a bad reconstruction. That's how this is supposed to go, right? So as input data, we take the entire spectrogram, and then for the purpose of our algorithm, we slice it into 1 second long chunks. So we subsample, and then we're using a sliding time window. So what you can see here is that this bit of the spectrogram overlaps with this here a bit. So this is what we feed into the autoencoder. And here we can see how those slices of the spectrogram are processed by the autoencoder. So in the first row, we see the input, and then the second row is the autoencoder's attempt to reconstruct this type of information. And in the third row, we see a comparison of the input and the reconstruction pixel by pixel. So black pixels show no difference between input and output, and bright pixels show that there is a problem in the reconstruction. So you can see visually that the reconstructions here work quite well, but then there are also some smaller problems kind of around this bit here. But yeah, generally this reconstruction works rather well. And when I say it works rather well, I mean in comparison to how an abnormal sound is processed. So if we look at an abnormal sound, this is the sound that we've talked about before. So we have a longer period of silence. We have only those 4 kind of more quiet beats. And we see that the reconstruction of those slices of the spectrogram is much more problematic. So it's something comes in quite noisy, and with a bare eye, you can maybe not tell the difference between them so well, but those error plots really show that we're having huge deviations between input and output. So this type of anomaly detection we want to use to actually diagnose whether the machine is doing well or not. So how do we do that? So we need to translate this anomaly information into a machine diagnosis. So we'll start with a normal sound. And this is really what we do. So let's hope this comes in. Okay, so this is the familiar spectrogram again. And now those reconstructions that we saw, you can aggregate that as a kind of mean reconstruction error per slice. And here you can see over time, along those time slices where the reconstruction has worked well and where it has worked not so well. So what we see in this plot is a threshold. So we need a threshold against which we compare the reconstruction. And if we're above the threshold, we're having a poor reconstruction. This is an abnormal sound, and this can indicate machine failure. That's the idea here. And to diagnose this entire sound, what we do is we take the mean of reconstruction errors that we have here and see where this mean sits in comparison to the threshold. So the mean of this trace here is indicated by this X marker, and we see that it sits left to the threshold that we've used. What you also see in this plot is where the reconstruction errors of the training data sit. So the training data was all normal, and the reconstruction errors that we found in the training data are the reconstruction errors that we find acceptable. So yeah, so this is a case where we predict that this machine is okay, despite minor problems around this irregularity right here. And we can now also look at the abnormal case. And in this abnormal case, we see that we're having really poor reconstruction throughout time, and the reconstruction error sits well above threshold. And this percentage here, by the way, means that it's larger than 99.2% of what we've seen in training. So yeah, this is the reconstruction. This is the machine diagnosis in action. And yeah, with that, I can conclude what we have done in our project, and we'll now only have a brief moment talking about the outlook. So yeah, so what we've achieved is good predictions to my mind on this one machine type that we focused on, which was the valve. So it's certainly on our agenda to explore how our approach generalizes to other machines. We're also looking into more advanced sequence models. So very simple sequence models did a very good job on doing anomaly detection here, but they were kind of slow. So obvious next steps would be doing transformers, which are just more performative, more efficient. And then we're also looking at the hybrid of having time-distributed convolutional autoencoders to also span the long time sequence. Then we also want to improve a little bit on the deployment, allow the users to upload just some kinds of sounds. And we're also looking into the role of background noise. So we've seen that the autoencoder has a way of smoothing the signal. So we see there's quite some potential in dealing with background noise better than other algorithms would do. And that's it. Many thanks to our mentors, Tristan Behrens, Adam Green, Davide, and Kevin for feedback on this presentation, Alberto, and all of DSR. So